So let's get back to the last 3 parts. It's gonna take like 15-20 minutes. Like these are just the main concepts of why we use the normal distribution and how can we apply that to explain the real world phenomenon. So, oh, by the way, I removed the green screen because it's too dark and it's not working. But it's dark. So let's say we have there's warp text. I don't have the clip, right? Yeah, let's go back to the clip that we have before. It was the clip that like if we have the carton board, actually should have like an image for that, like carton board, and if you drop enough number of beats, then it's gonna follow this nice curve. Okay. I mentioned that this is, if we actually compute in that curve in theory, it is the binomial distribution, which is discrete because you can list all the places that the beats can fall into. Like there are, like in this case, 8 slots for the beats. So that's finite. And we put the graph, then the bar graph, which just looks like what we have here. And this one is a binomial distribution. But actually, if we increase the size, the length, and also make sure that we increase the pegs, or that bars at the front that makes the beat go left or right. If we increase that to larger and larger, the result would converge to a normal distribution. By that I mean I don't have one. When n is 2, right, the binomial distribution will look like that. When n is 3, it will look like that, right? And 4, 5, 6, 7, and so on, hundreds and thousands. So eventually, when you plot a graph, it's gonna look like that. You're gonna see like a thin bar. Right. This is always going to be discrete, right? Because we fix where the beats can go. But the theorem, this the whole theorem, tells us that this if the number of rows, the number of slots is large enough, then that curve looks just like the normal distribution with some value of n. So now we connect the discrete case to the continuous case, and we can actually use them back and forth. But the actual computation for the normal distribution is difficult. If you want to find the probability that you toss 10 million coins and you get like 5 million coins, the actual computation will involve like having to sum up all the binomial terms, 1/2 to that or whatever, which is of course not fun. So we can just transform that image to the normal distribution and use the numerical values for the normal distribution to solve the original value about the binomial distribution. So let me show you how that works. So that's the statement. It's long, but let me break it down. So that's the binomial random variable. P is the chance of success, which is between 0 and 1. inclusive, and n is the number of trials. Like how many times we repeat the same experiment, or in this case for the beads, how many beads we put into that board. There's one condition that says if these two values are large enough, and when I say large, it depends on like what kind of branch you are working on, but 5 or 10 should be good enough if the product of NMP. So let's say if you talk about just the standard head or tail, P is 1.5, like let's say it's not biased, so we need n to be at least 10. If you flip coins at least 10 times, then this x can be approximate using the normal distribution instead. So let's say this curve, the discrete distribution curve will fit pretty nice with the actual normal curve. There's gonna be like some error, but they're gonna fit with new parameters. This is the mu, the average is n times p, the sigma square is n times p times minus p. So let's see in action how that thing works. Again, I forgot to erase all the text. It's supposed to be gone. So the question is gonna be like this simple. So let's say we toss a fair coin 20 times. You can toss 20 coins at the same time. What is the probability of getting between 9 and 11 heads? So the question is like just gonna be as simple as that. So if you use the applet or just like visualize the question, like since we throw 20 times, the center is gonna be at 10. The average of number of heads is 10. Then we want to find the probability that it's gonna be 9 between 9 and 11. So we are looking at these 3 bars, the sum of these 3 bars when the number of heads is 9, 10 and 11. So that's the question. If you go back to the binomial distribution, you can find the formula for each bar. I think the formula for that bar is, let's say 20 choose 9 plus 20 choose 10 plus 20 choose 11. Sorry, 20 choose 11. Everything times 1 to the 2 to the 20. That's the exact number. Right? But we can do that because we only have 3. What if we have 100, 10,000? We can't do that, right? But nevertheless, we can approximate using the random variable. So first we have to transform that. Right? We have to construct a curve that can approximate. Right? The white one is the binomial distribution with 20 trials and the chance of success being 1/2. This red curve here is the normal distribution with different parameters. Right. So first we have to determine what the parameters are. Oh, I'm missing the parentheses here. So we can just use that number, like that formula we got on last page. N is 20, P is 1/2. 20 times 1/2 is just 10. So that's 10. For the rest, we have 20 times 1/2 times 1/2. So that's 5. So now that we know that red curve will look like the normal distribution with mean 10 and with variance 5. Well, again, that's yeah, that works with 5 there. Okay. So if you want to compute that for the original problem about the binomial distribution, we can use this easier to compute normal distribution to approximate it. Okay. And the way we approximate that is, again, we have to transform that red curve into the normal distribution we transform the points 9 and 11 to some points here and there, and now we can approximate the area of the blue regions, like the middle 3 bars, by using the area under this curve instead, which is easier to look. So from the computation we get that these two points are actually like points 4 and minus 0.4. So the area of the this pink region is about 0.34. So that means we also have about like 0.34 chance to get between 9 and 11 heads. And of course that is going to be really close to the actual computation that we have. And that's the precise number. Okay. So we have we attack this problem in 3 steps. Right. First we transform the white curve to the red curve. Then we get the information of the red curve, and by transform that again to the green curve, which is the standard normal distribution. And oh, that's 2 steps, not 3. Sorry. Yeah, that's 2 steps. And that pink area, that amount, that the area of that pink region is gonna approximate the area of the blue region. Again, that's I'm not expecting you to like be able to complete the whole thing, maybe just part of it, but just to illustrate on why we have to study normal distribution. So we have 2 more concepts here. This oh yeah, for the rest of this slide we are not going to look at the exact number, just the concept. But of course I'm gonna put numbers there just in case. So this is the important one called the central limit theorem. So if we go back all the way to the normal distribution, we illustrate that by using the Carlton board. Right. We argue that if we throw enough number of bits, then the curve is going to follow the normal distribution. Sorry about the handwriting. Normal distribution. Right. But that is actually not the main explanation on why we define that particular curve as a normal curve. And this is the reason why we define that as a normal curve. So let's go to look at another clip. Then you better go watch yourself, or let me give you some sneak peek of that and just play. This looks very nice.
Somewhere in the fields, a brave helicopter much larger.
This is like very well done.
The distribution of
and it was like 6 years ago and only like 100k views. It should be at least 1 million. I don't understand world nowadays. But anyway, finish that clip. I will wait. Just hitting it on. Let's continue. If you want me to wait, just pause and come back later. Okay, there, right. So the keyword here is the mean of the means. Okay, what is the mean of the means? So if you have a coin, and you flip it and you count how many number of hairs are there. Right. Since it's just a single coin, it's gonna be like either 0 or one head, sorry. And then you can record your experiment. Right. Maybe the first one you get head, the second one you get tail, the third one you get heads, the fourth one you get tails, and so on and so forth. Right. So now you get one head, 0 head, 1 head, 0 head, and so on. So at the end of the experiment, so let's say you repeat that 10 times, you can find the average of number of heads. In this case, maybe it's something 0.7. You are lucky and get 7 heads, and you repeat the same experiment again. You start from 0, you flip heads, tail, and you find an average again. Maybe it's 0.6. You repeat again. Maybe next time you get 0.5, next time 0.8, next time 0.1, next time 0.9, and so on and so forth. So each of these values is a mean. The mean. This is a mean of a single experiment. But we can collect all these means and find the means of these means. Okay. Let's say that's like 0.7, 0.6, 0.5. If we sum these things up, let's say that's 10, 36. Oh, that's exactly 0.6. That's the mean of the means. Now this one is fixed at 10 coins, right? If we list all the if we plot the sampling distribution of this experiment, and we get something. Oh, let's substitute this thing. We will get something like that. Right. It's gonna look like the curve. Right, that's the mean. The mean, like the center is 0.5, which is the number we expect to see more often. Right, you get some 0.4, some 0.3. Yeah, so that's the mean of the mean. This is when you use 10 coins. If we increase that to let's say that's the case when 10 coins. Let's say we increase that to 20 coins, or in this animation they use 20 rabbits. Then the center is again still 0.5, but the curve now looks different. Right? Most of the time they are not too far away from 0.5, maybe 0.4 or 0.6. Right? For the first case, sometimes you get 0.9, you get 0.1, or you even get 1, or you even get 0. You can get extreme values on both ends. Not that hard, not that rare. But like for this one, it is rarer to get the extreme values. Like if you actually throw 20 coins, right, it's gonna be harder to get hits on all 20 coins. Like that's the chance. I want over 20, which is about 1 million ish. I think it's like 1, so yeah, whatever number it is, like it's 1 in a million to get all hits on 20 coins. You might see it, but it's gonna be rare. So now you repeat that again, but in each experiment, in a single experiment, you get 500 coins. Yeah. And this means most of the time you're gonna get like the value close to 0.5. You're not expected to get extreme values, but here you can say that it is also rare to even get the value 0.6. Right? It is common to get 0.6 here. You can sometimes get 0.6 here, but as you increase the number of the sample size, then it's getting rarer and rarer to get 0.6. All the values is gonna be very close to 0.5. And that's what it means to be the mean of the means. In each of these graphs, we compute the mean of the means, but we increase the number of sample size. So as we increase the number, we are gonna get a more accurate means. You can get fewer extreme values on both ends. All the values gonna be concentrated in the middle, which is the expected average here. So, oh yeah, it's there. I repeat that. So yeah, if the size is 1, you get either 0 or 1, or that's the coin flip other way. If you have 5 coins, you either have like 0 heads, 1 head, 2 heads, 3 heads, 4 heads, or 5 heads. If you increase that number higher and higher, and you get samples from this curve, it's gonna go to what we call the normal distribution. Okay, that's one concept. And the other one concept, this one is not an accurate graph, but the other one, which is kind of like mind-blowing, and I think they mentioned that in the clip, is that it doesn't matter what kind of distribution you start with. Eventually, everything, whatever it is, they are gonna be a normal distribution. If you compute the means of the means, then no matter what kind of distribution you start with, eventually they are gonna be normal distribution, right? That means you may have a binomial, a discrete binomial distribution. You may have a geometric distribution. You may have a Poisson distribution. You may have a uniform distribution. You may have an exponential distribution. You may have whatever. Even you can start with the normal distribution itself. And if you get samples, can you compute the mean of the means, then everything, all these things, no matter how skewed or how weird or how whatever it is, they are gonna be the end result. As the number of samples size increases, it's gonna look like the nice wheel shape we have. Mind blown, I hope. So this is the main reason why we pick this particular curve to be the normal distribution, because this is the curve that we get from the mean of the mean from this particular theorem. So let's go for the formal definition for a brief moment. Right. So we first let x be any random variable with some mean and some, again, standard deviation. We don't care about what the shape it looks like. We don't care about the mean. It can be 10 million, whatever. We don't care about that sigma. If n is large enough, right, if we get a large enough sample size of size n, then the end result, the means of that n samples, gonna form a nice normal distribution curve with new variables. That actually the previous variable. It means that the center is gonna be the same center as we have before. And this is one nice thing, right? It is intuitive, right? If you know that rolling a single dice have the expected number or the average of 0.5, then if we roll 10 million dice, the average should still be that same thing, like, because we just like get the average of all the averages. The average should still stay to be the same average that we had before. So this is what it says. And the other thing, this is going to be connected to the other theorem. The other thing is, oh yeah, I have to mention that later. But it means that this term guarantees that the average still stay the same if we repeat the experiment many times with large sample size. And oh yeah, just for a note, like, we require that the size is large enough, but what is large, like, again, is kind of a vague idea. Maybe if n is too large, then it's not practical. If n is too small, then it's not accurate. So we have to kind of balance between these two parameters. But in practice, as a rule of thumb, Like we need to have at least 30 samples. If you collect any data, make sure you get at least 30 samples. So that the sample you pick gonna give you the average that is pretty close to a actual average. If you pick just 1 or 2 or 3, it can be skewed to either the left or the right. If you pick enough, then that's gonna be close to average. If n is small, if the value is small, if like the cases are right, you can only have enough time or resources to pick say 10 samples, then that still works, but we have to use a different distribution. You cannot use the normal. Normal is nice. It has all the nice property. Everyone uses it. But if n is small, then that breaks. But nevertheless, we can use something else. It's called a student's free distribution, which we can just begin it. It looks like this curve, but it has different tables. It has different values, properties, and stuff. So it's not as nice as the normal distribution. So yeah. And lastly, law of large number. And this is a more common intuition, I believe. Like the law of large number. Say if we get large enough numbers, then the result should be close to the actual result. I mentioned that if the average is 3/5, then the average of like higher and higher sample size should also be close to 3/5, right? That guarantees the center of the average, but it doesn't guarantee that it's gonna be closer and closer to that average, right? Is it possible that if I roll 10 million dice, I gonna get average of 4? Right. Actually, it guarantees, but we have to analyze it a little bit more, right? We know it's gonna be 3/5, but it's not gonna be 3/5 every time, right? It's not like if I throw 10 million dice now, I get 3/5. If next day I throw another 10 million dice, I get another 3/5 sharp. Right? It's gonna be like if we go a little bit, maybe 3.51, 3.48. But can it be 4? Can we get large? But that's the question, and the answer is no. Right? By the law of large number, it says that the average is going to be very, very, very close to 5. Very close to 3.5. We are not gonna get a weird value if we pick enough. So let's start from the theorem. Like that's what we have here. If we increase n, like if n gets larger and larger, maybe a million, 10 millions, a billion, gazillions, then this whole thing is gonna get smaller. Okay, so if n is large, then 1/n is gonna be small, because it's the reciprocal. If n is 10 to the 10th, 1/n is gonna be 10 to the minus 10, 0.0001. It's gonna be small, and then that times some constant is also gonna be small, right? So what does it mean for that the latter part to be small, right? Remember that part is the variance. If the variance is small, that means the curve, most of the value of the curve, we're gonna get cluster. We're gonna get together in the center, and the tails here gonna be very abrupt. And maybe this is pretty accurate of the curve. Right? This happens when the variance or the standard deviation is small. Right? But this formula guarantees that if n is very, very large, then that is small. What it means for that to be small, then it means we are guaranteed to get a narrow curve. If n gets even larger and larger, then we get something like that, which looks kind of crazy. Like, let's think of for a moment. What it means is, let's just use the dice example. The average is 3.5. In this curve, maybe we get the average of 3.4, 3.6, plus or minus. This means if the average is 3.5, then maybe if we mark it to scale, maybe that's 3.4, maybe that's 3.6. Even if it's like just 0.1 apart from the center, this curve like that is very close to 0. So that means almost always you're gonna get value that is very close to 3.5. Maybe if n is large enough, you can even like guarantee that the you can even like guarantee that the mean is gonna be 3.5001 or 3.5999, right? And with an asterisk that exists almost always. Okay. So this is what the law of large number means. It means if we get a larger and larger sample size, then we can almost guarantee that the mean is gonna be that actual mean. It means that it's going to be closer and closer to the mean mu of x that we are given in the first place. So yeah, that's another formula for the theorem. So that's how we got the formula. This time we just like we just summarize as a statement. So we just have any random variable, and then again it can be anything. Right? It can be uniform, it can be discrete, it can be exponential, or whatever you start with. And if you take enough number of samples from that distribution, then the mean is gonna be close to mu. If you know the average is 3.5, then if we take 10 to the 10 samples, then the average is almost guaranteed to be exactly 3.5. The larger the sample size we get, the more accurate the estimation of the mean we get as well. So I think that's it. I thought I have another clip or two. Let's see if I'm missing anything. Oh no, I don't. Okay, so that's it for this week's class. So I will see you next week, I guess. Right? So stay safe. Don't go outside without mask or whatever. Bye.